I'd like to tell you about the Einstein telescope. The Einstein telescope does not exist yet. It's more like a dream, a sort of a moonshot project that may not be possible, somewhat like the Apollo program in the 1960s. But if we are to understand our very deepest cosmic roots, really where we come from ultimately, we must try and build the Einstein telescope. As you can already guess, the Einstein telescope is not a normal telescope. For one thing, it will be built under the ground, deep under the ground, hundreds of meters under the ground. And it will consist of a huge triangle of tubes, each about 10 kilometers long. And in these tubes, laser beams will move about, and they will measure the side of each of those triangular tubes to exquisite precision in order to measure signals of black holes in the universe. And as you can see, the Einstein telescope is a worldwide collaboration of scientists and engineers from all corners of the world. But the nugget of this project, the observatory where it might be located, may be here, near Liège. Isn't that amazing? How so? Liège, the city of Liège, it so happens that we are in the middle of what is called the Euregio-Meuse-Rhine. And the Euregio-Meuse-Rhine is traversed under the ground by a huge rock, the orange band here on the slide. And that rock is covered by 200 meters of soft soil. Now that happens to be exact the sort of underground we need in order to construct this observatory. But why is this called the Einstein telescope? It's because the seeds of this observatory were planted by Albert Einstein more than 100 years ago in the discoveries that Albert Einstein made about gravity. You see, Albert Einstein reimagined gravity. He imagined gravity as a manifestation of the bending and warping of the invisible fabric of space. The moon is kept in orbit around the Earth because the Earth slightly deforms the fabric of space. And likewise, the Earth is kept around the sun because the sun, the mass of the sun, creates a valley in the invisible fabric of space around us. And Einstein thought, wait a minute, if space can curve and bend and warp, then surely it can also vibrate. So Einstein thought there must exist invisible waves, gravitational waves, which, when they ripple across the universe, they slightly stretch and shrink distances as they go along. And so the Einstein telescope is not a telescope that's going to capture light. Obviously not, it's going to be under the ground. It's a telescope that's going to be designed to capture these elusive, invisible gravitational waves that Einstein predicted more than 100 years ago. And such waves, we now know, can be generated in the universe, for instance, when two black holes collide. That creates a burst of such invisible gravitational waves. And once they're generated, these waves travel across the universe. They travel at the speed of light. And they go through everything, through stars, galaxies, and also through our planet. And when they move through our planet, as you can see, it changes the diameter of our planet. It wobbles. But these waves, this is exaggerated, right? These waves are tiny. They only change the diameter of our planet by the width of a single atom. So you need an exquisite way to measure distances. And that's why you need these strange telescopes, long tubes, either an L-shaped observatory or a triangle, whatever. This is an observatory for gravitational waves in the United States. So how do you measure the length of these tubes to an accuracy of a proton? You do this by sending in a laser beam. When you send in a laser beam and you let it split, going through both arms and reflect with a mirror, and you arrange stuff so that both beams exactly annihilate, except when a gravitational wave passes and changes slightly the length of these two arms. When that happens, a signal escapes. And so it happened. About 10 years ago, this L-shaped observatory measured very briefly, a fraction of a second, a laser beam escaped from this observatory, from these two arms in this observatory. And that turned out to be the faint echo of the collision of two black holes in a galaxy far, far away, more than 1 billion years ago. We can read those signals. You see, Einstein's theory comes with an equation, a mathematical equation that relates this laser signal which we observe here on Earth to the source deep into the universe. So it's some sort of advanced pattern matching game, just like you do on your computer when you try to recognize cats. Now, the observation of gravitational waves, so this is how it goes. You change, the blue is the signal which we observe, and the yellow is you try to overlay the signal with using Einstein's predictions. And once you find a match, you can interpret what you actually saw. So the observation of gravitational waves, you should think of it as a Galileo moment of our time. 400 years ago, Galileo decided to point a telescope to the sky, and that was the birth of the astronomy we know. Everything we've learned about the universe for 4 centuries has come to us through light. We've discovered exoplanets, we've discovered other galaxies, we've discovered that the universe expands. It has changed our worldview. The observation of gravitational waves is opening a new kind of astronomy, a new window onto the universe. And every time mankind has done that, we've been surprised. Because in fact, most of the universe out there is dark. It's governed by dark matter, black holes, dark energy, all sorts of stuff where light is not involved, or regions where light does not reach. And so Einstein's telescope is going to be the spaceship of the 21st century, with which we will unlock that dark side of the universe, rewrite the history, opening up a whole new way of doing astronomy. So what can we ultimately hope to discover? What's the holy grail of this whole enterprise? I think in the end, as I mentioned at the beginning, I think in the end, it's about our deepest roots. You see, this is the history of the universe, from the Big Bang left to today right. And we've mapped out this history using light of all frequencies. But there's a limit. We can see far back in time, but we cannot see all the way back to the Big Bang. The early stages of the universe are hidden. They're hidden in the mist. It's like trying to see inside the sun. This doesn't work. But these gravitational waves, they go through everything. With gravitational waves, we can hope to really look all the way back to the Big Bang and see, understand, grasp how the universe truly came about. So what do we expect? Well, I thought about it. I thought about it for a long time with Stephen Hawking, because when I was a young boy, I was interested in these big questions about the universe, and I decided to go to Cambridge to study and work with Stephen Hawking. We found ourselves on the same wavelength, and we collaborated on studying the nature of the Big Bang for about 20 years, till he died in 2018. And this is pretty much how I found Stephen in his office in Cambridge, surrounded by books, a dysfunctional desktop, and of course, a picture of Marilyn Monroe on the wall. Stephen had already lost his voice back then, but he could talk through a speech synthesizer which was mounted on his wheelchair. And in the very first conversation I had with him, 20 years ago, this is what he asked me.
The universe appears designed. Why is it the way it is?
So, good luck with your next job interview. Stephen was obsessed with this question. And what he means here is that, well, down at the level of physics, at the level of particles and forces and composition of the universe, there's a mystery. All these particles and these forces of the universe seems to be designed, seems to be just fit, seems to have emerged from the Big Bang in such a way that billions of years later, life, biological complexity would become possible. What should we think of this? And so we developed a whole theory of the origin of the universe. You go back, far, far back in time, and the crux of our theory is that if you go back all the way to the Big Bang, even the notion of time and space get blurred. That's quantum mechanics into play. Time sort of turns into a space dimension, and in fact, the laws of physics in these earliest stages of the universe, we think are evolving themselves. It seems that in the earliest stages of the universe, there's sort of a deeper layer of evolution happening, a sort of branching tree, through which the physical laws that we observe, that we have today, emerged. So we came to some sort of Darwinian way of looking at the origin of the universe, and indeed that's how I describe it in my book, in which I describe my collaboration with Hawking. On the Origin of Time is, of course, a variation of On the Origin of Species of Darwin. And so this evolution, the key point now, is that these branchings, you should really think of the birth of new kinds of particle forces, new kinds of forces of nature. These are violent events that the universe underwent in its earliest stages. Well, some of these branchings go together with a huge burst of gravitational waves. Those gravitational waves are still around today, but they're weak. It's some sort of background humming of the universe, which we have not yet been able to hear. So those gravitational waves are fossils of that deeper layer of evolution which we have put forward. Catching these is the ultimate goal, I think, of what we can hope for with Einstein telescope. So this is my journey through time. We started out with a mathematical equation written down by Albert Einstein more than 100 years ago. That mathematical equation held the idea that there should be ripples, gravitational waves. And it held the idea that our universe must have had a beginning, a Big Bang. Hawking thought the Big Bang is hiding a deeper level of evolution. But in order to test this, we must build the Einstein telescope, a huge interdisciplinary collaboration of 100,000, or maybe 1,000 scientists and engineers working together. So we go from mathematics to a project which can be a marvel of international cooperation. And maybe that's the deeper message of Einstein telescope. As a telescope, it's about finding deeper truths of black holes and the universe. But in the bigger picture, it's a project that can bring us together, that can truly make us realize and understand how our planet and the universe or our home. What more can we wish for? So stay tuned. Thank you.